In this video, we'll look at a couple of different common syntheses that we use to produce either carboxylic acids or ketones with substitutions on the alpha carbon. And the first one that we'll look at is the Malonic Ester synthesis. And this is used to prepare carboxylic acids with alpha carbon substitutions. So that includes this type of molecule with a single substitution, or this molecule with two substitutions. And it involves use of diethyl malonate, which has these two ketones or two esters with the carbonyl groups beta to each other, so that this the protons on this middle alpha carbon are particularly acidic and can be easily removed, and the anion on that position will be stable, and we can use that for other reactions. So we'll go ahead and show one of the reactions using a malonic ester synthesis. Again, we start with diethyl malonate. It's a multi-step reaction. The first step is to react it with ethoxide in ethanol. Then we'll react it with propyl bromide. And I'll color code it so that it's easier to identify where the carbons come from. And then the third step is to react it with acidic aqueous solution in heat. And it will produce this carboxylic acid. In this case, we've got the propyl group attached to our alpha carbon. So it's a 1, 2, 3, 4, 5 molecule. It'd be pentanoic acid. And so just to help clarify what's going on in this set of reactions, I'll draw out each step one at a time. And so again, we start with the diethyl malonate. The first reaction is ethoxide in ethanol, and we use ethanol because we have these ethyl esters. So if we have a transesterification reaction, we don't change the diethyl malonate because we would be replacing one ethyl group with another ethyl group. But anyway, the ethoxide will deprotonate one of these two alpha protons, forming this anion. And this anion can be resonance stabilized by both carbonyls, making it more stable than a normal alpha carbon. And anyway, the next reaction is, I guess I'll draw it down here. Is to react that with our propyl bromide. And this will be an SN2 reaction between this anion and this carbon here to kick off that bromine and add these this propyl group to that alpha carbon. Then the next step, it will be reacting with it will be the acidic aqueous workup, and this will hydrolyze these esters. Forming this dicarboxylic acid. And then the final step is one we haven't seen before, but it's decarboxylation, where we will actually lose a CO2 because one of these carboxylic acids will fall off as CO2 and will form this pentanoic acid as our organic product. And so because we've seen the mechanisms for all of these steps except the decarboxylation, we'll show how decarboxylation occurs so that we see all of these mechanisms. So the decarboxylation can occur if we have two carbonyls beta to each other, and one of those carbonyls must be an acid, a carboxylic acid. But if these conditions are met, then we can lose one of those, we can lose that acid carbonyl as CO2. So if we look at the molecule from the previous reaction, then essentially if we rotate around this bond, so we put the hydroxyl group up here, and we form this hydrogen bond between this carbonyl and this hydrogen, then what can happen is the electrons from this bond can come down, the electrons here can move over, the electrons here move up, not up to the oxygen, but they grab that proton, then we form this enol plus the carbon dioxide. And of course, the enol will exist in equilibrium with the, it's enol-like, really, because it has two hydroxyl groups. But anyway, it'll act just like an enol, and it'll exist in equilibrium with the carboxylic acid. So it will, once we form this enol-like compound, it will convert to the carboxylic acid pretty easily, and we'll lose the other carboxylic acid group as a carbon dioxide. Now we can also, just for your information, we can also hydrolyze those esters using basic conditions. And so we'll review the reaction steps under acidic hydrolysis. So the first step is reaction of the diethyl malonate with the ethoxide in ethanol. The second step is the alkyl halide reaction. The third step will be the acidic aqueous workup. If we wanted to do basic hydrolysis of the ester, the first step would be the same. Ethoxide in ethanol, followed by the alkyl halide, followed by the basic hydrolysis, which hydroxide in water with heat. And then to convert, because this would give us the carboxylate instead of the carboxylic acid, we still have to do an acidic aqueous workup in order to convert that to the carboxylic acid and do the decarboxylation. And so the basic hydrolysis requires 4 steps instead of 3, but it's good to know that we can do this with either acidic hydrolysis or basic hydrolysis of the ester. So the next reaction that we'll look at is pretty similar, but it's used to form ketones instead of carboxylic acids. Specifically methyl ketones. And we use not diethyl malonate, but a beta ketoester. And again, we will take this beta ketoester and it's another multi-step reaction, but the steps are essentially the same. We use ethoxide in ethanol, followed by an alkyl halide, and I'll color code it again. This time we'll use ethyl bromide, and then acidic aqueous workup. We could do the basic ester hydrolysis followed by acidic aqueous workup, but I'll just show this because it's fewer steps. And we'll get this 2-pentanone as our product that will add this ethyl group onto the alpha carbon. So we'll add these 2 carbons to our ketone. And we'll go through what happens at each step of the reaction. So again, we start with the beta acetoacetic. The ethoxide in ethanol will deprotonate at this middle alpha carbon to form the enolate. Once we have the enolate, we'll react that with the ethyl bromide. Once we have this compound with the ethyl group attached, then we can do. I'll just draw it down here. Either we can do the acid hydrolysis or the basic saponification reaction. That will convert the ester to the carboxylic acid. And then we'll decarboxylate to lose this carboxylic acid and leave us with the ketone. And so again, it's very similar to the Malonic Ester synthesis we looked at before, but this is an acetoacetic ester synthesis. So now we'll use the malonic ester synthesis and the acetoacetic ester synthesis in a few reactions to show how they work or what we can do with them. So in the first one, we'll look at the malonic ester synthesis to produce this carboxylic acid with a cyclopentyl group. And this will actually involve two additions to our alpha carbon. But the second one will be intramolecular rather than intermolecular. And so again, the first step is ethoxide in ethanol to deprotonate this alpha carbon. The second step will be a dibromide. 1, 2, 3, 4. Then we'll use another ethoxide in ethanol step, followed by acidic hydrolysis. And let me color code these carbons. So these 4 carbons in the cyclopentyl ring come from this 1, 2, 3, 4 carbons in this dibromide. So that the alpha carbon comes from the diethyl diethyl malonate. But anyway, just to review just to show the individual steps in this reaction. Again, we have diethyl malonate We react that with ethoxide in ethanol. Getting our enolate. Once we have the enolate, we react that with the dibromide. And in this case, our enolate will attack one of these two carbons, kicking off bromine. And attaching this alkyl bromide to our diethyl malonate. So then the next step that I'll draw down here is to react this again with ethoxide in ethanol, and that will remove our other alpha proton and produce another enolate. So in this case, it's an intramolecular reaction. These electrons will attack that carbon, kick off this bromine. And we form this 5-membered ring. And then the next step would be hydrolysis. And then decarboxylation. And we would form our final carboxylic acid product. The most important steps being our first reaction with the alkyl halide, and then the intramolecular reaction with the alkyl halide. And so we can get these two reactions by essentially repeating the enolate formation with the ethoxide and ethanol. So now we'll do an intermolecular disubstitution using the acetoacetic ester synthesis. So again, this is a multi-step reaction. The first step will be the ethoxide in ethanol, followed by reaction with ethyl bromide, followed by ethoxide in ethanol, followed by reaction with methyl bromide, followed by the acidic hydrolysis, and will form this substituted methyl ketone. And we'll again go through these steps to show how we get there. So again, the first step is ethoxide in ethanol. Form the enolate. Then we react that enolate with the ethyl bromide. Then we'll take this compound, react that with ethoxide in ethanol again. Almost forgot my alkyl group. But yeah, we have another enolate. That enolate will react with, in this case, we'll use methyl bromide. And we'll attach, we'll have this ethyl group and this methyl group attached to this compound. So again, we'll have the hydrolysis and decarboxylation to form our final ketone. I have one more reaction I want to look at, and it's more of a retrosynthesis problem. And so we have a carboxylic acid, and it's a disubstituted carboxylic acid. We have this methyl group, and we have this 1, 2, 3, 4, this butyl group attached to our alpha carbon. And because we have a substituted carboxylic acid, we know that we need to do the Malonic Ester synthesis. In order to produce that carboxylic acid. And so in order to get from here to here, we can outline the necessary steps that we'll start with our diethyl malonate. We know the first step will be to react that with ethoxide in ethanol to form our enolate. The second step will be the addition of one of these alkyl groups. And so let's choose methyl iodide first. I don't think the order matters, but we'll add the methyl group first. The third step will be another reaction with ethoxide in ethanol to form the enolate again. The fourth step will be the addition of the other, that's 1, 2, 3, 4, 1, 2, 3, 1, 4. Yeah, this butyl group, we'll use butyl bromide for that to add our other alkyl group. And then the final step will be an acidic aqueous workup to hydrolyze and decarboxylate the diethyl malonate, forming this carboxylic acid. And I won't show the individual steps because we've seen all of these reactions before in the previous reactions, and so you should be able to interpret these individual steps on your own. So yes, that's how we can use these beta dicarbonyl compounds to form methyl ketones and carboxylic acids with either one or two substitutions at the alpha carbon.